Welcome to another podcast. In this episode, we're going to be taking a look at another example involving method of undetermined coefficients. Although this time I want to introduce something called the superposition principle. We've talked about the superposition principle before, and it's sort of a byproduct of the fact that we were working with linear differential equations. And so for this particular example, I want to be looking at the following equation. We're going to look at y double prime minus 3y prime plus 2y equals 3e to the negative x minus 10 cosine of 3x. And so I just want to show you what generally we're looking at here. I'm going to call this function f1 and this function f2. And then if I use the operator form of the equation, in other words, this is d squared minus 3d plus 2 applied to the function y, if I call that L, then this equation in operator form is simply Ly equals f1 plus f2. Now, what is our strategy for trying to solve this? Well, it turns out the strategy for solving this is pretty simple. I'm going to find one solution y1 that's equal to f1, and I'm going to find a different solution y2 that's equal to f2. In other words, I'm going to have to solve two problems here. It then turns out that if I get L of y1 plus y2, the linearity of the operator will allow me to look at each one separately, and if they're equal to f1 plus f2 in this case, then I know that y1 plus y2, when operated on by L, gives f1 plus f2, which is exactly what we want to see in this case. So that's going to be our strategy. I'm going to have to solve two problems. First problem, second problem. Let's concentrate on the first problem here, which is Ly equal to 3e to the negative x. So I'm going to find a trial solution, which I'm calling y1 in this case. The trial solution, since this is an exponential, should be another copy of the exponential with a different constant. We can quickly look at the derivative here is going to be negative a e to the negative x. And if I take two derivatives of it, I'm going to get the negative to reverse itself. So I'm back to y1 at that point. If I then plug those into the differential equation, y double prime is a e to the negative x minus 3 times y prime plus 2 times y. And all of this will equal, I want it to equal f1, I want it to equal 3e to the negative x in this case. So I need to determine the value of a that makes the two sides equal. I'm going to factor out an e to the negative x and look at what remains. I get a plus 3a plus 2a e to the negative x equals 3e to the negative x. Simplifying over here, I get 6a needs to be equal to 3. The coefficients need to match up. So a turns out to be 1/2. All right, so that's a good start. That says that my solution to this problem is y1 equals 1/2 e to the negative x. So there's the solution to problem 1. That's done. Okay, let's try problem 2 now. So problem 2, I'm looking at Ly equal negative 10 cosine of 3x. And so if you looked back at the previous video, the trial solution here should be arbitrary linear combination of frequency 3, cosine, and sine. Okay, that says then, so this is my y2, sorry. So that then says that y2 prime would be minus 3a sine 3x plus 3b cosine 3x. And then y2 double prime So I'm going to take another derivative of this. Is going to be minus 9a cosine 3x and minus 9b sine 3x. Now, there's an easy way and a hard way to go about trying to finish this out. Let me explain what they are. Since I've written out y2, y2 prime, and y2 double prime, my suggestion to you when you work this is to do what I'm about to do. I'm going to add these together using the coefficients from the problem. So for example, I'm taking 1 times the double prime. So it's 1 times this. And then I'm taking, for y prime, I'm taking negative 3. So negative 3 times this. And then for y2, I'm taking 2 times this. So what I want you to do is I want you to add down. If I look at y2 double prime minus 3y2 prime plus 2y2, that should be equal to negative 10 cosine 3x on the left. And on the right, watch what happens when I add down. So let's start with, probably the easiest way to do this is to start with everything that's multiplied by a cosine. So if I look at all of the pieces multiplied by cosines, they're coming from here, here, and here. So let's put those all together. I've got a 2a from this piece. I've got a minus 3 times 3b, so that's a minus 9b on that piece. And then it looks like down here at the bottom I've got a 1 times minus 9a, so it's minus 9a cosine of 3x. Okay? What about the things that are multiplied by sine? Well, I'm going to add to that. We've got a 2b from the first. We've got a minus 3 times negative 3, so that's a positive 9a from the second. And then on the last one, we've got 1 times negative 9b, so minus 9b on that one. What should each of these be equal to? Well, if I look at this first problem, on the left-hand side is negative 10 is the coefficient of 3x, cosine of 3x. So this piece should equal negative 10. And there is no sine, so the coefficient of sine should be 0. Together, these create an equation, or a system of equations, if you will. That system of equations is, if I'm looking here, 2a minus 9a is negative 7a. Minus 9b, that needs to equal negative 10. And then from the bottom piece, I've got a 9a and a 2b minus 9b, so that's a minus 7b equal to 0. So this is a system of equations, 2 by 2 system, which we would solve the way you remember from high school, Algebra 2. This one, just for the sake of space here, if you do this correctly, you'll get a is 7/13 and b is 9/13. So that says that my y2 is, coming back over to where my trial solution was, a cosine 3x. So that's 7/13 cosine of 3x plus b sine 3x. Together, this forms the second problem. And if I want the overall solution, I take y1 plus y2. That is a particular solution. So y sub p, the particular solution for this problem, is y1 plus y2 that I ended up with here. Because this part will satisfy f1 and this part will satisfy f2. And so this process of solving two different problems, one problem for the first forcing function, a second problem for the second forcing function, using method of undetermined coefficients on both, this is an example of what is called the principle of superposition. This is a consequence, and the reason I can do this is because of the operator L that I discussed at the beginning of this operator L is a linear operator, which means it can be distributed. If you multiply by a scalar, you can pull the scalar in and out. And the reason that L is a linear operator is because the derivative D is a linear operator. And so as long as I'm doing linear operations with the derivative, then everything I showed you here is okay. So this is another example of how to use method of undetermined coefficients, and it's just a little bit more complicated forcing function for this particular example. All right, thank you for watching.